In a previous lesson on counting, we went over the basic methods of counting consisting of the OR and AND rules, as well as tree diagrams. In this lesson, we are going over additional counting methods, combinations, and permutations. To understand the difference, we are finding the number of combinations of objects when we select objects, while we find the number of permutations when we arrange objects. But how does selecting differ from arranging? When you select, you are not considering order in your selections, which means selecting A then B is the same as selecting B then A. While when you arrange objects, you are choosing your objects while taking order into account, which means selecting A then B is different than selecting B then A. For example, if I have 3 people named X, Y, and Z, if I take them to help me pick up boxes, the order they are selected in would not matter, thus forming one possible group to help me with the boxes. While if I wish to appoint from these 3 people a president, a vice president, and a secretary for a committee, then the order would matter, and I would have 6 possible ways to make the appointments, as taking X as president and Y as vice president is not the same as taking Y as president and X as vice president, for example. Let us start with combinations. Remember, combinations do not include order in the selections. Suppose I have n total objects, out of which I need to select R objects. The number of possible combinations is the number of groups of R objects I can form. The total number of combinations is given by this formula, n factorial divided by R factorial times n minus R factorial. Recall that the factorial of a natural number n is the product of consecutive integers from 1 to n. For example, 1 factorial is 1, 2 factorial is 1 times 2, which is 2, 3 factorial is 1 times 2 times 3, which is 6, and so on. And by convention, 0 factorial is 1. Now going back to combinations. Suppose I have a class of 10 students, out of which I need to select 4 students to organize a field trip. Here the total number is n equals to 10, and the number of selections is R equals to 4. The context here does not include order in selections, as I'm only selecting those students to organize a trip, and it wouldn't matter which one of the students is selected before the other. Then the total number of groups is given by the combinations of 4 out of 10. Using the formula would yield to 10 factorial divided by 4 factorial times 6 factorial. Now you could evaluate that right now using your calculator if you have access to one. But without your calculator, you could evaluate that by starting to expand 10 factorial into the product from 1 to 10. Notice that at the numerator, the product from 1 to 6 is the same as 6 factorial. So those cancel out, leaving us with 10 times 9 times 8 times 7 divided by 4 factorial. And 4 factorial being the product from 1 to 4, 2 times 4 at the denominator cancel out the 8, and 9 divided by 3 is 3, which leaves me with 210 possible combinations. Then there are 210 possible groups of 4 students I can form out of the given 10 students. Without using the formula, you could evaluate that combination immediately on your calculator using the expression 10C4. Now moving to permutations. Remember, permutations include order in the arrangements formed. But permutations could be done with repetition or without repetition. What does that mean? Suppose I have this set of digits from 1 to 5. How many 2-digit numbers can I form? Here we have order as 2-digit numbers, 12 and 21, for example, are not the same. And we have repetition because two-digit numbers can have repeated digits like 11, for example. So a two-digit number is formed by a tens digit and a unit digit. For the tens digit, I have 5 possibilities, as I have 5 total digits I can choose from. For the unit digit, I also have 5 possibilities as repetition is allowed, so I still have the choice to choose either one of the given digits. Now, using the AND rule, also known as the product rule, I end up with a total of 25 possible two-digit numbers. Now 5 is the total number of objects given, and I'm arranging two objects out of the given objects. Then my final answer 25 can actually be written as 5 squared, 5 to the power of 2. Generalizing that, if I have a total of n objects, out of which I'm arranging r objects with repetition, then the total number of permutations that can be formed is n to the r. But what if we are arranging without repetition? Considering the same set of digits from 1 to 5. Now how many two-digit numbers with different digits can be formed? Here, order still matters, but we can have repeated digits. Numbers like 11 and 22 are excluded from the outcomes I'm looking for. Again, I have room for a tens digit and a unit digit. I have 5 possibilities for the tens digit, as I can choose any one of the given 5 digits. But I have 4 possibilities for the unit digit, as I cannot take again the digit I chose for the tens digit, as repetition is not allowed. Using the product rule, I end up with a total of 22 digit numbers with different digits. As I have a total of 5, and I'm arranging 2 digits out of the given 5 digits, my final answer 20 is denoted by the permutation of 2 out of 5, P 2 out of 5, where P denotes a permutation without repetition. Using your calculator, you can input 5p2 to retrieve the 20 possibilities. Let us try to retrieve the formula for P now. We know that a combination of 2 out of 5 which exclude order in the selection is 10, which makes sense as when you exclude order you have less possibilities. Since P2 out of 5 is 20 possibilities, then C2 out of 5 can be seen as P2 out of 5 divided by 2 factorial. So P2 out of 5 is C2 out of 5 times 2 factorial. If we generalize taking the total as n and the number of selections as r, we obtain PR out of n is CR out of n times r factorial. Recall the formula for combinations. Multiplying that by r factorial cancels out the r factorial at the denominator, leading to PR out of n equals to n factorial divided by n minus r factorial, which is the formula used to find the number of permutations without repetition. Now, what are arrangements? Suppose I have 5 different books on a shelf, and I wish to arrange all of them, which means in how many ways can I place those different 5 books on that shelf? In this context, order matters, as I'm changing the order of placement of the books on the shelf. And I have no repetition, as I cannot place 2 books in one position. Order and no repetition imply a permutation, PR out of n. Here n is the total number of objects, which is 5, and since I am arranging all 5 books, then r is also 5. Applying n and r to the formula leaves me with 5 factorial divided by 0 factorial. And 0 factorial being 1, I end up with 5 factorial, which is 120. So an arrangement of n objects is the same as permutations without repetition with n equals to r. So an arrangement of n objects yields n factorial possible outcomes.